Welcome back to part 2 of week 6 of pre-calculus. We have finished a number of examples where we were talking about inverse functions. In this last example, the original function f was x minus 1 raised to power 3. As we explained, this function is bijective, meaning it is injective. It passes the horizontal line test. And it is certainly surjective because the image of this function is the entire real line. As we know, being bijective means that it has a unique inverse, and as we explained, the unique inverse of this function is the cubic root of x plus 1 function. We did check that g of f of x equals x for every x in R. All right, let us now talk about the relationship between domain and range of f and its inverse. Suppose f is bijective, so it has a unique inverse. Look at this picture. The potato on the left is the domain of f, the potato on the right is the range of f or image of f, and f moves or maps elements from the domain to those of its own image. But f inverse works in the opposite direction. And it's clear from this picture that the potato on the right, which is the image of f, is also the domain of the inverse of f. Much like the potato on the left, which is the domain of f, is also the image of f inverse. So there is this close relationship between the domain and image of a function and its inverse. There is, however, a variety of situations where things can go wrong, and here is this nice example that I want to show you. Suppose we start with function square root of x, which is defined on the set 0 infinity. And we had this before. Clearly, the inverse function is x squared. And it's easy to check. If we apply g to f of x, right, f of x is root x. So g of root x is simply root of x squared, and that is x for every x for which this makes sense, namely for every x non-negative. What if we reverse the situation? What if we now start with the function x squared and defined on the entire real line? Should the inverse function be root x? Let's see. If we try root x for g and try to compute g of f of x is x squared. Now g applied to x squared is square root of x squared. But square root of x squared is not necessarily x. It's the absolute value of x. And absolute value of x for a general x is not necessarily x, right? Absolute value of x only equals x if x is non-negative. What happens in this situation? It's easy if we visualize this. Here's our function x squared, And here is what happens. You can see immediately it doesn't pass the horizontal line test. If I intersect the graph of x squared with the horizontal line, like this, I see immediately that for a fixed y, when it's positive, there are two corresponding x's, positive root y and negative root y. And that is a problem. That is the reason why, in this case, our function x squared doesn't have an inverse. There is no unique value that corresponds to a fixed y. When you move real numbers from the domain of x squared to, for example, you can take the image of this function. To make it surjective, you can take the image to be non-negative numbers. But for any y here, there are in general 2 points, positive root y and negative root y. And f will map both to y. So when you start thinking about the inverse function, you have a problem, because f inverse at y must be simultaneously root y and negative root y. And for a positive y, root y and negative y are distinct numbers. So we come to a very important idea here. How do we go about this problem? How do we go about the problem of x squared not having an inverse? The idea is very generic, and we will use that idea later on when we define the inverses of trigonometric functions. The idea is to restrict the domain of the original function, to make it something smaller, so that on the new restricted domain, our original function becomes injective and passes the horizontal line test. So the function we are considering is x squared, and when defined on the interval 0 infinity, that doesn't pass the horizontal line test. So we restrict the domain of f so the function becomes injective. I can show you two ways how to do that. One way is the following. Instead of considering the function x squared on the entire real line, we can consider x squared defined only for non-negative real numbers. They'll correspond to the right branch of the parabola. what happens then? Then, if our function g is defined as root x, we have g composed with f of x as g of x squared, and g is the square root of x squared, which is still absolute value of x, except that now, because x is non-negative, absolute value of x actually equals x. And so the function g so defined is indeed the inverse of f. This time f passes the horizontal line test. Note that in this case, domain of f is the interval from 0 to positive infinity, r greater than or equal to 0. And that is also the image of the function root x. The image of the function root x is all non-negative real numbers. And likewise, domain of f inverse, which is also the set of non-negative real numbers, is the image of our function f. The image of f is all non-negative reals. But that's not the only way to restrict the domain of the function x squared defined everywhere on the real line. We could go the other way and restrict the domain to be the set of all negative or non-positive real numbers. So that would give us the following thing. That is the graph of x squared in the case when x is non-positive. I claim that in this case, our function is bijective when viewed as a function from the set of non-positive real numbers to the set of non-negative real numbers. And so it will have a unique inverse, and I claim that in this case, this unique inverse is negative square root of x. Let's see why. G composed with f of x is g of x squared. But then g of x squared is negative root of x squared. Root of x squared is absolute value of x. but because x is non-positive, absolute value of x by definition is negative x. And so we do get that g of f of x equals x. And note, just like before, we have this correspondence between the domain and range of f and its inverse. Domain of f is all non-positive real numbers. And that is also the image of the inverse function, because the inverse function here is the function negative root x. And its image is precisely all non-positive real numbers. And likewise, the image of f is all non-negative real numbers. And that is also the domain of the inverse function, right? The domain of negative root x is all non-negative real numbers. So one more time, it will be very often the case that the functions we're looking at are not injective. And so the inverse won't exist. Like the inverse doesn't exist for the function x squared when it is defined on the entire real line. I apologize, that was a mistake. That was meant to be negative infinity, infinity. When x squared is defined on the entire real line, it's not injective, and therefore it doesn't have an inverse function. The idea that we used was to restrict the domain of our function from the entire real line to something smaller. For instance, reduce it to the set of non-negative real numbers or to the set of non-positive real numbers. Then our function becomes injective, and that injective function, viewed with appropriate codomain, so that it's also surjective, will be bijective and therefore having a unique inverse. When we restrict x squared to the domain non-negative real numbers, the inverse is root x. And when we restrict the domain to be non-positive real numbers, the inverse is negative root x. That is a very important idea. Restrict the domain of a given function so that it becomes bijective. And as a bijective function, it now has a unique inverse. And one more time, we already said it, there's a clear relationship between the domain and the image of a function and its inverse. Also, it's easy to see that whenever an inverse exists, we have these relations. F inverse at f at x equals x, well, that's the very definition of inverse, and vice versa. F of f inverse of x equals x And this here is a typo. It should be image. And it also should be image. This is easily explained by the picture on the previous page. When you first apply f to some x and then apply f inverse, you go back to where you began. And vice versa. If you first apply f inverse, if you first apply f inverse and then apply f, you again get to where you began. All right, let's look at some examples involving tables and functions. In this example, for instance, we're given a function defined by a table. So we immediately see that f at 60, which is the first question, is 50. And f inverse at 60, presumably f inverse exists. F inverse at 60, it is such a value that at that value, f will be 60. Well, f is 60 whenever its argument is 70. Therefore, f inverse at 60 equals 70. In general, it's very simple to obtain the inverse of a function given by a table. All you need to do is simply flip the two rows. So this function gives f as a function of t. F is measured in miles, t is measured in minutes. So when we think of this as distance between some two objects at time t, then the inverse function will give t as a function of f, time as a function of miles, and I could write it as m for miles, t for time, and all I need to do is to flip the two rows. So the first row will be 20, 40, 50, 60, and 70. And the corresponding values in the second row will be 30, 50, 60, 70, and 90. So what is the meaning of f at 60 being 50, for instance? It means that after 1 hour, the distance between the two objects is 50 miles. What is the meaning of saying that f inverse of 60 is 50? Excuse me, f inverse of 50 is 60. What is the meaning of that? It means that when the distance between the two objects is 50 miles, it must be 1 hour after we started observing the two objects. Presumably, of course, that the distance at no two times can be the same. That is to say that a function f is injective when the distance is 50 miles. It must be exactly 60 minutes after we begin our observations. So to find the inverse of a function defined by a table, all you need to do is really just to flip the two rows of the table. And similar reasoning is applied when we have a function given by a graph. Function g here is given in the figure, and we see that presumably function g passes the horizontal line test, and viewed with an appropriate codomain, it's also surjective, so it has an inverse. We see that the value of g at 3 is 1. Now, what is the value of g inverse at 3? G inverse at 3, it's a value such that g at that point is 3. So we should consider the horizontal line y equals 3. We see that that line intersects with the graph at the point 5, 3, and so g inverse of 3 equals 5. Since g at 5 equals 3. Let us now summarize how we find the inverse of a function given by a formula. We pretty much did this already multiple times, but let's just summarize this. Well, first of all, you need to ensure that your function is defined in such a way so the inverse exists and is unique. So your function is defined from x to y. Make sure your function is injective on its domain and surjective. So you want to make sure that the image of f is all of y. If not, you can typically reduce y to take y to be just the image of f. Being not surjective is usually a smaller problem than being not injective. If you're not injective, you will need to restrict the domain of your function to make it injective. It's written here. Your function may possibly need to be restricted to make it injective if it's not already injective. A function that's not injective doesn't have an inverse. Being injective is necessary to have an inverse. Then you simply solve the equation f at x equals y for x. We already did this in the past. Let me show you that example. Remember, in this example, when we were trying to understand the image of the function 1 over x plus 2, we equated 1 over x plus 2 to y, and solved that equation for x, and understood that as long as y is not 0, that equation has a solution for x. That's exactly what needs to be done in general to find the inverse of a function given by a formula. You solve the equation f at x equals y for an arbitrary y, you solve it for x. And then typically for simplicity, we interchange the roles of x and y. Here is one example. The Celsius temperature as a function of Fahrenheit temperature satisfies this formula, 5/9 times F minus 32. Find the inverse function T inverse and express Fahrenheit as a function of Celsius. So we're given C as a function of F. We want to compute F as a function of C. So following this summary, I need to equate my function T of F, which is 5/9 times F minus 32 to an arbitrary y, in my case C, and solve this for F. Solving this for F, I get the inverse function T inverse. And solving this for C, I get 9/5 C plus 32. Note, by the way, that we didn't check in this particular case that our function T was injective and surjective. It definitely was, because this is a straight line, 5/9 times F minus 32. On the F C plane, this is a straight line with slope 5/9. So it certainly is injective, it passes the horizontal line test, and it is surjective because the image is the entire real line. So we didn't have to check this. But there are situations, of course, like in the example on the next page, where you have to be very careful and you have to certainly check whether the function you are working with is bijective. Consider, for example, the function 2 minus root x. Let's see if we can understand if that function has an inverse. Well, the domain of that function seems to be simply the set of all non-negative real numbers. And if you draw the graph, root x looks like this. So negative root x looks like this. and then negative root x plus 2 looks like this. The question is, where will it intersect the x-axis? That will happen at point 4 because root 4 is 2 and 2 minus 2 is 0. So my function looks like this. Our function does pass a horizontal line test. Now, what about being surjective? Well, if you view this function from 0 infinity to the entire real line, if you take codomain y to be the entire real line, it definitely won't be surjective, but we can just take codomain y to be the image, which is the set of all real numbers that are less than or equal to 2. And so viewed from x to y, this function is injective. And surjective, and therefore bijective. And so it has a unique inverse. To find it, all we need to do is equate the expression of our function 2 minus root x to y, and now solve this for x. Well, as we know, y has to be in the image, so y cannot be greater than 2. To solve this for y, we write 2 minus y equals root x, because y is less than or equal to 2. It's safe to raise both sides of this equation to the second power. And we're done solving this for x. If we interchange x and y, we see that f inverse of x is 2 minus x squared, or which is the same x minus 2 squared. What about restrictions on x here? Well, because x is the old y, x must follow the same restrictions as the old y. X here is in the domain of f inverse, which is the same as the image of f, which is the interval from negative infinity to 2. And so that is a parabola x squared shifted by 2 units to the right, and then we only need the left branch of that. So we have graphed both functions, f and its inverse. That, excuse me, was f, not f inverse. So again, when you're looking for the inverse of a given function, you have to be very careful. Before you start doing algebra, always make sure your function actually is bijective. If it's not, think if it could be made bijective. If you could work on domain and codomain to restrict them, restricting the domain might result in the function becoming injective, and restricting the codomain might result in the function becoming surjective. Once your function is both injective and surjective, it will have a unique inverse. All right, this example is finished. An interesting property of the graphs of a function and its inverse is that the two graphs must necessarily be symmetric about the line y equals x. What does that even mean? Symmetric about the line y equals x. Well, that means that if you have the graph of one function, the graph of the other function will look in such a way that whenever you take a point on the graph of f, for instance, and imagine like there is a mirror along the line y equals x. If you reflect that point on the graph of f about the mirror y equals x, so you put a perpendicular line through that point perpendicular to line y equals x. The point on that line that is at the same distance as it is from the original point on the graph of f will be on the graph of f inverse. The graph of f inverse is the mirror image of the graph of f when the mirror is located along the line y equals x. We will work out this in a minute. Let's establish this fact in the examples we have seen so far. For example, here when f equals 2 minus root x, that is the example we just worked on. We do have the two functions, x minus 2 squared when x is less or equal than 2, and 2 minus root x when x is non-negative, symmetric about the line y equals x. They, of course, intersect at the point, all three of them intersect at the point 1, 1. And you can see that whenever you take a point on the graph of one of these, they're mutually inverse to each other. If you take a point on the graph of x minus 2 squared, the mirror image of that point will be on the graph of 2 minus root x. They're symmetric about the line y equals x. The mirror image of that point 1, 1 is itself. It belongs to both graphs. The mirror image of the point 0, 2 is this point 2, 0. The mirror image of the point 4, 0 is this point 0, 4. This line joining 0, 4 and 4, 0 is perpendicular to the line y equals x, and moreover, the midpoint of that segment joining 0, 4 and 4, 0 lies exactly on the line y equals x. That point actually is 2, 2. And in all other examples that we worked in the past, you can see a similar situation. For instance, for the graph of x squared restricted to the non-negative real numbers, the inverse function was, as we established, square root of x. And the two graphs, x squared for non-negative x and root x, are certainly symmetric about the line y equals x. This point in particular where all three intersect is again 1, 1. In the other situation, when we restricted the domain of x squared to all the non-positive real numbers, we obtained that the inverse of our function was negative root x. And again, the two graphs are symmetric about the line y equals x. The point negative 1, 1, for instance, is symmetric to the point 1, negative 1. That is a very important property. But let us explain why this is true in general. Let me add a page. So we are explaining the following thing. We're explaining that if a function f has an inverse, unique of course, then the graphs of f and f inverse are symmetric about the line y equals x. A picture should be helpful here. So if say this is the graph of f, this here is the line y equals x, then this here will be the graph of f inverse. We need to prove that they are symmetric about the line y equals x. So the argument is the following. Suppose a comma b is a point on the graph of f. Which means, of course, that f at a equals b, which in turn means that f inverse at b equals a, which in turn means that the point b comma a the point with coordinates b comma a lies on the graph of f inverse. Our goal is to explain that a comma b and b comma a are symmetric above the line y equals x. All right, how do we explain that? How do we explain that a comma b and b comma a are symmetric above the line y equals x? Well, that amounts to two things. We first show that the line that passes through a comma b and b comma a is perpendicular to y equals x. How to show that two lines are perpendicular, we know. Their slopes must multiply to -1. How to find the line passing through a comma b and b comma a, we also know. And second, we show that the midpoint of the segment joining the points a comma b and b comma a, let me draw that segment. Let me not make it at the passing through the origin. We will show that the midpoint of that segment passing through a b or joining a comma b and b comma a lies on the line y equals x. That will establish that this distance equals this distance. This distance equals this distance. And so the 2 points are indeed symmetric about the line y equals x. So what is the slope of the line that passes through AB and BA? The slope of that line is, let's say this is the first point, this is the second point. Difference of y coordinates over difference of x coordinates. Old y coordinate, new y coordinate minus old y coordinate over new x coordinate minus old x coordinate. That is clearly -1. And in fact, the equation of that line, we don't even need it. We don't even need the equation of that line. The slope of the line y equals x is 1. The slope of the line joining AB and BA is -1. They do multiply to -1. And as we know, that implies the two lines are perpendicular. Just for the sake of completeness, I want to write down the equation of that line. The equation of that line is, using the point slope form of that line, y equals slope a minus b over b minus a times x minus a plus b. That is if you use that point. And the second thing that we show how do we find the coordinates of the midpoint of that segment? Let's say, I don't want to draw it because I don't know where it is. Let's say the midpoint has coordinates alpha, beta. How do we find in general the coordinates of the midpoint of a line segment whose endpoints have coordinates x1, y1 and x2, y2? Well, the x-coordinate of the midpoint is the average of the x-coordinates of the endpoints, and the same for the y-coordinate. The y-coordinate is the average of the y-coordinates of the endpoints. In our case, that means that alpha is a plus b over 2 and beta is b plus a over 2. And since one equals the other, since alpha equals beta, the point alpha comma beta lies on the line y equals x, as desired. So indeed, the 2 points are symmetric about the line y equals x, and therefore the 2 graphs are symmetric about the line y equals x. For each point on the graph of f, there is one and only one point that is symmetric to the original point about the line y equals x. If, for example, we get back to the graph of example 9, where we need to reconstruct the graph of f inverse looking at the graph of f, we see that the graph of f seems to have 2 asymptotes. Vertical asymptote x equals 0, and horizontal asymptote y equals 2. So when we reflect these two about the line y equals x, what do we get? What is the reflection of the y-axis about the line y equals x? Clearly, the reflection of the vertical axis about the line y equals x is the horizontal axis. So for f inverse, y equals 0, the x-axis will be a horizontal asymptote, as x equals 0 is an asymptote for f. The reflection of x equals 0 about the line y equals x. which is y equals 0, will be an asymptote for f inverse. Similar reasoning should work for the line y equals 2. What is the reflection of the line y equals 2 about the line y equals x? Well, it seems it is the line x equals 2. X equals 2 is a reflection of the line y equals 2. About the line y equals x, and y equals 2 is a horizontal asymptote for f, comma, it follows that x equals 2 is a vertical asymptote for f inverse. So f inverse has two asymptotes, vertical asymptote x equals 2 and horizontal asymptote y equals 0. Now, what will the graph of f inverse look like? Looks like 1, 0 is a point on the graph of f, so 0, 1 will be a point on the graph of f inverse. 2, 1 is on the graph of f, so 1, 2 will be on the graph of f inverse, and so on. So the graph of f inverse will look like this. And you can see the graph of f inverse does look symmetric to the graph of f about the line y equals x. Okay. How about this nice question? Think of any function that is equal to its own inverse. F such that f equals f inverse. Well, if you think about it, one such function is 1 over x, defined, of course, on all non-zero real numbers. F inverse is actually itself, because if you compute f of x, you actually get x for every x in the domain. One over x is one such function. Another class of functions that satisfy this property is functions constant minus x. They're linear. Constant minus x, where c is constant. Domain is, of course, the entire real line. The image is the entire real line. These are functions whose graphs are straight lines with slope -1. If you compute f at x, of course you get x. And so f inverse is also c minus x. Think if you can find other examples of this kind. Other examples of functions that are equal to their own inverses. Let me show you two more simple examples of finding inverse functions in functions that will involve radicals. Let's start with the function 5x cubed plus 1. To find its inverse, as we know, we need to check that this function is bijective, which it clearly is. It's a transformed cubic parabola. It's injective, passes the horizontal line test, and the image is the entire real line, so it's bijective. That's good news. And when we equate this to y and solve this for x, you can easily see that x here will be cubic root of y minus 1 over 5. And therefore, interchanging x and y, we see that the inverse function is cubic root of x minus 1 over 5. And you can see the graph of that function on the left in red. Indeed, the two graphs are symmetric above the line y equals x. There's a point where they intersect. I don't know what that point is, but the point where they intersect is necessarily the point where all three, the two graphs and y equals x, intersect. The two graphs can't intersect at a point that doesn't lie on y equals x because of the symmetry condition. And the other example here is the function x minus 2 squared minus 3. That's a parabola, y equals x squared, shifted 2 units to the right and 3 units downward. It is therefore not injective in general. Not injective when viewed on the entire real line. So to make it injective, we have to restrict the domain. You can alternatively see what happens if you forget to check for injectiveness and simply equate this expression to y. and start solving for x. Well, here x minus 2 squared is y plus 3. Assuming that y is greater or equal to negative 3, so that y plus 3 is non-negative, we take square roots. But then you have a problem. You are taking the square root of a square, so there will be absolute value. Absolute value is the plus minus, depending on the sign. So you get that x minus 2 equals plus minus root y plus 3. And so x equals 2 plus minus root y plus 3. It is because of this plus minus, because you can't decide whether you should take plus or minus, this function doesn't have an inverse. Just like in one of the examples we had in the past, there are two ways to restrict that function to obtain an inverse. Remember, we restricted x squared to non-negative reals and got one inverse, root x. And then we restricted the same function x squared to non-positive real numbers and got another inverse, negative root x. We will do something similar here, and we will end up with different inverse functions. So there are two ways how we can restrict the domain of f to make it injective. So f has an inverse. Right now it doesn't because it's not injective. One way is to say that the domain of our function is the right branch from 2 to infinity. When we do that, we have immediately x equals two plus square root of y plus 3. Right? These are the x's that are greater or equal than 2. Square root is, of course, non-negative, so these x's are greater or equal than 2. In this case, f inverse is 2 plus root x plus 3. X is greater or equal than negative 3. This is the graph in red in the picture. This here in red is the graph of the function f in, well, let me not write f inverse, 2 plus root x plus 3. But we could as well have restricted the domain of our function f to be the left branch, which is from negative infinity to 2. In which case, we would have had x to be 2 minus root y plus 3, These are the x's to the left of 2. And in this case, the inverse function will be 2 minus root x plus 3. Again, x is greater or equal than negative 3. It would be nice to have a graph of this last function. We can easily draw it. We can start with root x. We can then shift it to the left by 3 to get root x plus 3. To get negative root x plus 3, we reflect, flip about the x-axis, and then finally to get 2 minus root x plus 3, we shift upward by 2 units. So we will get a function that starts at the point negative 3, 2. It will intersect the x-axis at the point 2, 0, because when x equals or maybe not 2, 0, maybe at point 1, excuse me, at point 1. Because when x equals 1, we get 2 minus root 1 plus 3, that's 2 minus root 4, that's 2 minus 2, which is 0. That is the graph. So in fact, in the picture, that'll be just a thing symmetric to this picture in red. It will pass through the point 1, 0, and you can see that this branch in purple is symmetric to the dashed branch of the parabola. The point 2 comma negative 3 is symmetric to the point negative 3 comma 2. The point 1, 0 is symmetric to the point 0, 1 through which this parabola passes. Correct? F at 0 is 0 minus 2 squared minus 3. That's negative 2 squared. That's 4 minus 3 is 1. So it does pass through the point 0, 1. And they are indeed symmetric, 0, 1 and 1, 0. about the line y equals x. Again, in general, the purple branch is symmetric about the line y equals x to the dashed branch of the parabola. These are brothers. Much like the red curve is symmetric to the non-dashed branch of this parabola. It would be nice to think about this question that just came to my mind. At what points do the graphs of f and f inverse in either of the two situations? Intersect. There are two such points. There's one point here, and there's another point here. It would be nice if we could find their coordinates. It's an interesting question. Think about it. All right, and we finish here our discussion of inverse functions, and the next topic will be exponential functions. Thank you. Bye-bye.